Chapter 14 is going to take a very in-depth view of acid-base equilibria. In this first part, we'll spend some time reviewing previous concepts we've already covered about acids and bases. It's very important to be able to distinguish between a strong acid and a weak acid. A strong acid is one that fully dissociates or ionizes in water. It'll break up 100% into ions, therefore it's a strong electrolyte. The abbreviation often used for a strong acid, just a generic any strong acid, is HX. So if we were going to write the equation for HX in water, we would have our strong acid plus H2O, and we would use a single arrow. Single arrow because a strong acid fully ionizes. The proton of the acid would be donated to the water, and we would form H3O plus, which is the hydronium ion. And we would be left with X minus, which is the anion from the strong acid. So when you have a strong acid, that ionization or dissociation occurs 100%. And all we have left at the end of the reaction are the ions that are present. This is kind of the longhand way for writing that dissociation of an acid. You might also see this shorthand notation where we say we have strong acid HX and we write aqueous after it for showing that it's in water, and then we use that single arrow and we show that it breaks up into H plus, which is aqueous, and X minus, which is aqueous. A lot of times H plus, which is called a proton or a hydrogen ion, is used interchangeably with H3O plus, which is called the hydronium ion. The hydrogen ion doesn't exist as H plus in water, it actually exists as the hydronium ion. But oftentimes this shorthand notation of writing the dissociation of an acid is used where it just shows H plus. So you're going to want to know that those two things are used interchangeably, and the equation on the right is kind of the shorthand notation of writing the full ionization of the acid in water on the left. So how does this change if we have a weak acid? A weak acid is often abbreviated with HA instead of HX, and it will partially dissociate in water. It contains mostly uncharged molecules, and there will also be a small amount of those ions. Therefore, weak acids are also weak electrolytes. So if we were to write HA, or weak acid, plus H2O, we would now use equilibrium arrows to represent the ionization of this weak acid. The proton of the weak acid would be donated to the water, and we'd form H3O plus, and we'd be left with the anion from that acid, or A minus. So if we were going to write this as our shorthand notation, we would say HA, aqueous, breaks up into the hydrogen ion plus A minus, both of those ions being aqueous. And in this case, we don't have 100% ionization, we have that partial ionization taking place. So at equilibrium, we're going to have a mixture of everything in here, and most of it is going to be that molecular acid that's combined together, and we're only going to have a small amount of the ions. There are three major acid-base theories: Arrhenius theory, the Bronsted-Lowry theory, and Lewis theory. If we look at a pyramid, Arrhenius theory is at the top. This would be the theory that we learned previously last semester. It's at the top of the pyramid because it's the most restrictive of things that can be acids or bases. In this chapter, we're going to mostly use Bronsted theory, which is short for Bronsted-Lowry. And then next chapter, we'll learn Lewis theory. Lewis theory opens up a lot of species that can be acids or bases. That's why it's at the bottom of the pyramid. Many things that we've never considered being an acid base before could actually be considered acids or bases using Lewis theory. So a reminder of what Arrhenius theory says: an Arrhenius acid is a substance that produces hydrogen ions or hydronium ions, whatever one you like to use, in water. Specifically, the definition says it has to produce that hydrogen ion in water. So water has to be the solvent for an Arrhenius acid. So when we wrote our dissociation of our strong acid and we had our acid in water, that was how we could qualify it as being an Arrhenius acid. An Arrhenius base is a substance that produces hydroxide ions, so OH minus, and also in water, where water is still the solvent, if it's going to be an Arrhenius base. A lot of the strong bases that we would have seen before were metal hydroxides that we dissolved in water, and they broke up into their metal cation and that hydroxide anion, so they were hydroxide ion producers. The metal hydroxides were typically group 1A and 2A metals from the periodic table. Our definitions change a little bit about what an acid or a base can be according to Bronsted theory compared to Arrhenius theory. A Bronsted acid is a substance that can donate hydrogen ions, or it has a proton that it can donate. A Bronsted base is a substance that can accept hydrogen ions. It has something on it that will allow it to accept a proton. The Bronsted theory doesn't say anything about the solvent being water. So this opens up other species now that can be acids or bases compared to Arrhenius theory. An Arrhenius base had to produce hydroxide ions. A Bronsted base doesn't have to produce hydroxide ions. It just has to be able to accept protons or hydrogen ions. So for example, if we were to consider we had some weak acid, and we'll call it HA, and we reacted it with a base. So we have an acid-base reaction here, where HA is our weak acid and B is our base. Our base has to contain some lone pair of electrons on it to be able to accept a proton from our weak acid HA. So imagine that your base uses its lone pair of electrons to grab that hydrogen ion from the acid. And when it grabs that hydrogen ion, it doesn't take any electrons with it because it's taking H+. So the electrons contained within this covalent bond right here stay with A. They stay with that A term there. So our products then will be the base grabbed a hydrogen, so now it's BH, and it took H+ with it, so this species will develop a positive charge, it'll be BH+. Plus we're left with A, and A will develop a negative charge because those electrons in that covalent bond stayed with A right there. So the base always abstracts a proton from the acid, not the other way around. But in order for it to be an acid, it had to have a hydrogen that it could donate in the first place. And that was how we identified if something was an acid last semester, was did it have a hydrogen out front? If it had a hydrogen out front, we knew it was an acid. Whenever you draw out a Lewis structure, if it has a hydrogen, it could potentially be an acid. And if you draw a base and it has a lone pair of electrons on it, it could potentially be a base. Also notice that the products of any acid-base reaction are also another acid and another base. So when our base picked up a proton, now it has a proton and it could potentially act as an acid. So this species is an acid, and A- actually has a lone pair of electrons left over on it from that covalent bond staying with it, and so A- could be a base. Species that differ by one proton are considered pairs. So B and BH+ are a pair. They're called conjugate acid-base pairs, where if B is the base, then BH+ is called its conjugate acid. And our acid HA, its pair would be A-. Those two species differ by one proton. And if HA is the acid, then A- would be its conjugate base. Next, we're going to practice showing the transfer of a proton from an acid to the base by using Lewis structures. This is the acid ionization for a strong acid in water. So we have hydrochloric acid, or HCl, and if we draw its Lewis structure, the chlorine has 3 lone pairs of electrons on it, and it's reacting with the water itself. So we can draw our Lewis structure for water. The HCl is our acid in this case, so the water has to be our base. And we're going to use a single arrow for this reaction because our acid is strong. So that means the base will have to grab a proton from our acid. The lone pair of electrons on the oxygen is going to be the starting point for grabbing that proton off the acid. The electrons are highly electronegative, and they'll take that proton, and then those lone pair of electrons, the electrons that are in the covalent bond there, will stay with the chlorine and become a lone pair of electrons on it, because the water or the base is just abstracting that hydrogen ion. So what we form then, when water picks up a proton, it becomes hydronium ion, H3O+. It has one lone pair of electrons still on the oxygen, and it's a positively charged species because that oxygen has a positive formal charge. And the other species we form is the chloride anion. Now our chlorine has 4 lone pairs of electrons around it, and it has a -1 formal charge. So looking at our names of these two species that we formed, our water became hydronium, which would be its conjugate acid, and those two would represent a pair. And the chloride anion would be the conjugate base of our hydrochloric acid. So those two would represent a pair. There's always going to be an acid-base conjugate pair, 2 of them, that you can identify in each ionization equilibrium. The acid-base pairs are species that differ by 1 proton. Next, let's try the same thing, but for a weak acid in water. Recall that we wrote that generic equation for HA, which was just any weak acid with a base, but now we're changing our base to actually being water because that's the reaction that's taking place. So HA could maybe be something like hydrofluoric acid, which is not a strong acid, plus H2O. If HF is our acid, then water must be our base. Definition of a Bronsted base is a proton acceptor. A Bronsted acid is a proton donor. So our base is going to accept a proton from the acid. It grabs that proton, and those electrons in that covalent bond stay with the fluorine. Our products, and we're going to use double arrows because we have a weak acid, so it'll be an equilibrium that will develop. But our products are going to be water plus a proton, so that is the hydronium ion, H3O+, plus the anion from that acid, which will be the negatively charged fluoride anion. So our conjugate acid-base pair here, water was our base, its conjugate acid is hydronium ion, and HF was our acid, and its conjugate base is going to be the fluoride anion. Let's look at how our equilibrium will change if we put a weak base in water. So in this case, we have ammonia, which is NH3, and we're going to make a solution of that in water. So we have H2O that will react with NH3, and we can draw the Lewis structure of ammonia, and the nitrogen has a lone pair of electrons on it. And since it's a weak base, it's not one of our metal hydroxides, it's not strong, we will use double arrows. In this case, we're being told that our ammonia is acting as the base. So by default, the water this time must be acting as the acid. So if the water is acting as the acid, then it's going to donate one of its protons, and the ammonia is going to accept it. Ammonia can accept a proton from water because it has a lone pair of electrons on the nitrogen. So it can grab one of the protons from water, and then the electrons in that covalent bond will stay with the oxygen. So we form, in this case, a protonated ammonia, which it had 3 protons initially, and now it will have 4. And it picked up a proton, so now it's going to have a +1 charge. So this is ammonium ion, NH4+. Plus, what are we left with when water loses a proton? We now just have OH Now there's 3 lone pairs of electrons on oxygen, and it'll have a negative charge. This is the hydroxide anion. So we knew that strong bases were often hydroxide donors. Weak bases often produce hydroxide ion in water, but there's not a ton of hydroxide in ammonium. There's a mixture of everything. So it's got an equilibrium that it establishes. So in this case, the water was our acid, and water's conjugate base will be the hydroxide ion. So those two species are a conjugate acid-base pair. And ammonia was our base, and so in this case, ammonia's conjugate acid will be the ammonium ion. So those two are a conjugate acid-base pair. There are a lot of species that could be Bronsted bases. A Bronsted base just has to be able to be a proton acceptor. In order for it to accept a proton, it needs to have at least 1 lone pair of electrons on it. So water could technically accept 2 protons. It has 2 lone pairs on it. Fluoride ion has 4 lone pairs around it. Ammonia, we just saw, has 1 lone pair on the nitrogen. Hydroxide has many lone pairs around it as well. The number of lone pairs don't indicate how many protons it will accept. Usually each of these species will just accept 1 proton, but they all have at least 1 lone pair of electrons that are available to take a hydrogen from an acid. This list is just a reminder of the common strong acids and strong bases you want to be familiar with. All of these species listed will undergo 100% dissociation in water. So they break up fully, and we only use single arrows when we write them. So the strong acids are often perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and sulfuric acid, which we learned sulfuric acid was the only diprotic acid on the list because it had 2 hydrogens that it could lose. And the strong bases are group 1A and 2A metal hydroxides. So lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. So this time, without actually drawing out Lewis structures, let's practice writing balanced equations for the dissociation of the following acids in water, and then labeling the conjugate acid-base pairs. So in the first one, we have HNO3, which is nitric acid. And we're being told that this species is going to act as our acid. And nitric acid is a strong acid. It's on our list of strong acids. So when we put it in a flask with water, the water is going to function as the base. The base would be the proton grabber, the proton acceptor, and the acid would be the proton donor. So we're going to use a single arrow to write this out because we have a strong acid, and our products will be H3O plus, we got that hydronium ion for 1, and the conjugate base of our acid will be that anion we're left with, which would be NO3 minus, which is the nitrate ion. So it kind of helps to remember some of those polyatomic ions from last semester as well. Hydronium ion is going to be an acid, and that will be the conjugate acid that will pair up with water. And nitrate is going to be the conjugate base of nitric acid. So those two would be the other acid-base pairs. In B, we have acetic acid. And acetic acid is not on our list of strong acids. So therefore, if it's not on the list of strong ones, we know it's got to be a weak acid. And we're told we're writing these dissociations in water. So in this case, water is going to be our base. We're going to use equilibrium arrows to represent the dissociation of our weak acid. Water will grab a proton from acetic acid and form hydronium ion. Plus we'll be left with, when acetic acid loses its proton, a little bit of its anion, which is acetate, C2H3O2 minus. It's important to have the charges correct on your species that you form from your acid-base reaction. So we have our conjugate acid, hydronium, that pairs up with water, and our conjugate base, which is acetate in this case, that's going to pair up with our acetic acid. Let's try a few more examples doing the same thing. We're given 3 different acids. We're going to write the equations for the dissociation in water and label all conjugate acid-base pairs. In A, we have HSO4-. This is the hydrogen sulfate ion. And hydrogen sulfate can function as an acid. It has a proton that it can donate. So in water, this is going to be our acid. Water is going to be our base. And HSO4- is not on our list of strong acids, so it must be weak. So we'll use double arrows. Water will grab a proton from the hydrogen sulfate ion and form hydronium. Plus, when HSO4 loses a proton, it already had a minus charge, but remember that lone pair of electrons stays with the anion portion. So it'll become SO4-2- now, which is the sulfate anion. So we're going to have our conjugate acid-base pairs. Water's conjugate acid is hydronium. Our conjugate base of the hydrogen sulfate ion is going to be sulfate. And so that'll be our second pair. In B, we have NH4+ that we're starting with. And so we're given an acid in each case. So that's the ammonium ion, which can function as an acid. It has 4 protons that it could possibly donate. Plus, it's going to react with water, our base. So our base is a proton acceptor. It's going to take one of the protons from our acid. We also need double arrows again because it's a weak acid. When our base is water, we always form hydronium ion. And what are we left with when NH4+ loses a proton? We're left with ammonia, NH3, which is a neutral species in this case. So because we started with something that had a positive charge, when it lost a proton, NH+, it now had a conjugate base that was neutral. So we have our conjugate acid-base pair with water and hydronium, and then we have our conjugate base of ammonium, which is ammonia. In our last example, we have HCl, which hydrochloric acid is a strong acid. So for this reaction with water, we would have a single arrow that we would use. We would have our hydronium ion when the water becomes protonated, and our anion we'd be left with would be our chloride. So we're going to have our conjugate acid and our conjugate base. And those would be the pairs, using lines to connect between the individual conjugate acid-base pairs. We saw that the reaction of an acid with a base always produced another acid and another base. So on one side of our equilibrium, we're going to have a stronger acid and a stronger base. And on the other side, we're going to have a weaker acid and a weaker base. It doesn't mean that the stronger acid and stronger base are always on the left and the weaker are always on the right. They could be flip-flopped. But no matter what, one side will contain 2 that are stronger and 2 that are weaker. And if we're starting with equal concentrations of reactants and products, the reaction will be favored based upon who the stronger acid and base are. The stronger acid wants to donate a proton more, and the stronger base wants to accept that proton more. So it's more likely that the stronger acid and stronger base are going to react more so than the weaker acid and weaker base going back and reacting. Therefore, the equilibrium will always be favored on the side of the weaker acid base pair, essentially. So what we often do is we draw an arrow in the direction of the favored reaction. So the arrow is pointing towards the weaker acid and the weaker base. It's longer pointing in that direction, showing that's the direction that's favored. So at equilibrium, there would be a greater concentration of the weaker acid and weaker base present, and a lesser concentration of the stronger acid and stronger base present, because those two reacted away to form the others. In order to figure out the direction of the favored equilibrium, we need to be able to identify which acids and bases are stronger than others. So we often use something known as an acid-base ionization chart. This is just a short, truncated chart of the full version that you're going to want to print off on Blackboard. You will be given that full version on any quiz or exam. So it's important that you use it throughout the entire chapter and always have it by your side. You're going to want to practice using it a lot so you feel confident. On one side, on the left, you have acids. On the right-hand side, you have bases. As you go from bottom to top on the acid side, the acids are getting stronger. At the very top, notice these are where our strong acids are. They undergo complete ionization in water, meaning they ionize 100%. So we have our perchloric, our sulfuric, all those acids that were listed as our strong ones. The hydronium ion is kind of then used as a benchmark. It's relatively strong, and that's the conjugate acid of water. Everything essentially below hydronium going down is considered a weak acid. And there are many more acids on that full chart on Blackboard. The order that they're listed in tells us how strong or how weak they are. So the higher up on the chart, the stronger the acid. The lower down on the chart, the weaker. Water is also kind of used as a benchmark. So water can function as an acid, we saw. It's not normally an acid, normally it's a base because it's fairly weak, but it can be an acid with the right things because it has a proton out front. These things below water essentially are not going to ionize in water at all. So these are really weak acids at the bottom down here, such as ammonia, hydrogen, methane, ethanol. They typically don't like to function as acids, but they can with the right stuff. On the right-hand side of this chart now, we have our bases. And the bases are the opposite trend as the acids. As we go from top to bottom in this case, the bases are getting stronger. So the weakest bases are at the top. In this case, if we look at water as a benchmark, these bases that are above water are weaker than water as bases, and they do not undergo ionization in water. So the conjugate bases of strong acids are really weak bases. They're so weak that if they're in water, they don't react with the water and go back to form acid. So that's why with strong acids, they undergo ionization completely. So conjugate bases of strong acids are very, very weak bases. And then using water as a benchmark, going down this way, those bases are starting to become stronger bases than water itself. So the conjugate base of water is hydroxide ion, and that's kind of another benchmark on the chart. These bases below hydroxide are very strong. These undergo complete ionization in water. They will react with water. So sulfide, ethoxide, amide, hydride, methide, these are very strong bases. And very strong bases have extremely weak conjugate acids. So ethoxide ion is a really strong base, but its conjugate acid, ethanol, is incredibly weak for an acid. So there's an inverse relationship on this chart between acid strength and then its conjugate base, or base strength and its conjugate acid. And remember, those species, if they're a pair, they only differ by one proton. So let's practice using our acid ionization chart. Which acid is not stronger than HF, which is hydrofluoric acid? And we have A, perchloric acid, B, hydrochloric acid, C, carbonic acid, and 3, phosphoric acid. So first we want to identify where hydrofluoric acid is on our chart, which HF is right here. And if they are stronger than hydrofluoric acid, they're going to be above it. So perchloric acid is above it, hydrochloric acid is above it, phosphoric acid is above it. That leaves us with only one that is not higher than it on the chart, which is H2CO3 carbonic acid. So carbonic acid would not be stronger than hydrofluoric. Rank the following acids by their strengths from strongest to weakest. We have ammonium ion, hydroiodic acid, hydrofluoric acid, hydrocyanic acid, and acetic acid. And then after we rank them, which acid has the strongest conjugate base, which acid has the weakest conjugate base. So we're going to need to use our acid ionization chart. First, let's identify where all the acids are. So we have NH4 plus ammonium ion right here. Hydroiodic acid, that's strong, that's going to be at the top. Hydrofluoric acid is a weak acid. Hydrocyanic acid is also a weak acid. And acetic acid, which is a weak acid. So now that we identified them, the strongest acid is going to be the highest on the chart. So hydrogen iodide in water would form hydroiodic acid, which is going to be our strongest, followed by hydrogen fluoride, which would be hydrofluoric acid in water. Then acetic acid, ammonium ion is the fourth, and hydrocyanic acid would be the fifth. So from strongest to weakest, we ranked them now. And answering the next part, what acid would have the strongest conjugate base? Remember, there's an inverse relationship between acid and conjugate base strength. So the strongest conjugate base is going to come from the weakest acid. And our weakest acid was hydrocyanic acid, HCl. So its conjugate base is down here, which is the cyanide anion, Cn-. And we're increasing in base strength as we go from top to bottom. So that one will be the strongest conjugate base. And which acid would have the weakest conjugate base? The weakest conjugate base would come from the strongest acid, which our strongest acid was number 1, HI, hydroiodic acid. And hydroiodic acid's conjugate base is going to be iodide ion, I-, and that's way up there at the top on the base side, so it's very weak for a base. So its conjugate base would be iodide. Next, we're going to predict the products and still label our acid-base conjugate pairs, but we're going to also use our chart to decide what direction we should draw the arrow longer in. So what direction will that reaction be favored in? And the first one we have sulfuric acid plus ammonia. So sulfuric acid is a much stronger acid than ammonia could be as an acid. You'll notice you'll find NH3 and H2SO4 both on the acid side of your chart. But since H2SO4 is higher on the left-hand side, then therefore it's going to trump in strength and end up being the acid, which will then make NH3 have to function as the base. So our base will be a proton acceptor from our acid, so we'll form ammonium ion, NH4 plus, when it grabs a proton. And when H2SO4 donates a proton, we'll be left with HSO4 minus, or that hydrogen sulfate ion, where ammonium is the conjugate acid of ammonia, and hydrogen sulfate is the conjugate base of our acid, sulfuric acid. So now if we just look at our two acids and compare them in terms of their strength, we have sulfuric acid versus the other acid, which is ammonium. And if you look at your chart, sulfuric acid is much higher up on the chart than ammonium is. So the sulfuric acid is our stronger acid, and the ammonium is our weaker acid. Next, we could also compare our bases individually. So using the right-hand side of our chart now, identify where ammonia is as a base and where hydrogen sulfate ion is. Ammonia is farther down on the right-hand side, and HSO4 minus is up really high on the right-hand side. So that means that ammonia is our stronger base, and HSO4 minus is the weaker base. So in this case, our stronger acid and stronger base are going to want to react more so to form more weaker acid and weaker base at equilibrium. So we would draw the arrow longer pointing towards the weaker acid and weaker base. We draw it pointing towards the right-hand direction in this one. For the next example, we have SO42 minus, we have that sulfate ion, reacting with HCO3 minus. So notice that SO42 minus doesn't have any protons that it could donate at all. So that one has to be our base because it doesn't have a proton. Whereas HCO3, hydrogen carbonate ion, will have to be the species that's acting as our acid because it has a hydrogen ion that it could donate. When our acid gives up a proton to our base, we'll form HSO4 minus hydrogen sulfate ion. And when our acid loses a proton, we'll be left with CO3 2 minus now. So we went from -1 to -2 because we gave up a hydrogen ion, which is the carbonate. So we have our acid-base pairs. Sulfate conjugate acid is going to be hydrogen sulfate ion, and hydrogen carbonate's conjugate pair is going to be the carbonate ion. That'll be its conjugate base. So now we want to pick our two acids or our two bases to check on the chart. The stronger pairs will always be on the same side. The weaker pairs will always be on the same side. So you really only have to check either both acids or both bases. But let's say that we want to check our acids. So we're going to check HCO3 minus as an acid and HSO4 minus as an acid. And looking on our chart, the hydrogen sulfate ion is much higher on the left than the hydrogen carbonate is. So this would be our stronger acid, and hydrogen carbonate is much lower, so that's the weaker acid between the two acids. And we could also check the bases too. You'll notice that carbonate is lower on the right-hand side, making it the stronger base. And sulfate is the weaker base. So when this reaction takes place, the hydrogen sulfate and the carbonate are going to combine more to form at equilibrium a greater amount of sulfate and hydrogen carbonate. So our arrow is going to point away from our stronger pair towards the weaker pair. The direction of the favored equilibrium would be to the left. Let's try another example. We have HF, which is hydrofluoric acid, plus ammonia. So we're going to have our acid plus our base. Our base will take a proton from our acid and become ammonium ion. Our HF will lose a proton and become fluoride ion. This is going to be our conjugate acid, and fluoride will be our conjugate base. Those two will be our pairs. And now let's look at both of our acids individually using our chart to see who's a stronger acid. So we want to identify where HF and where NH4 plus is on the same side under the acid. And HF is much higher on the left side than NH4 plus, so HF would be our stronger acid. And ammonium would be the weaker acid. And without even looking, we can say then that our weaker base would have to also be fluoride anion. And our stronger base is going to be the ammonia because the two pairs are always going to be on the same side. So our favored direction for equilibrium, we'll draw our arrow longer pointing towards the right, pointing towards the weaker acid-base pair. And in our last example, we have NO2 minus, which is nitrate, reacting with HCN. So HCN has a proton it can donate, whereas NO2 minus doesn't have anything that it can donate. So the NO2 minus is going to be a base, and HCN will be the acid. When HCN gives up its acid, we're left with cyanide, CN minus. And when the nitrate grabs that proton from our acid, we form HNO2. So we're going to have our pairs. If HCN is our acid, then CN minus is the conjugate base. And NO2 minus is the base. So HNO2 is its conjugate acid. Choosing either both the acids or both the bases, I often choose to look at the acids, HCN, and then the other acid will be HNO2. So finding them both on our chart. So between nitric acid and hydrocyanic acid, the nitric acid is higher on the acid side, so that will be the stronger acid, and the other one will be the weaker acid. And so that means that the cyanide would also be the stronger base. If we were to look on our chart and compare CN minus on the right-hand side to NO2 minus, you'll see that CN minus is lower on the right, which means it's the stronger base. And NO2 minus is higher, which means that it's the weaker base. So our direction for the favored equilibrium, our arrow we draw longer pointing to the left, pointing towards nitrate and hydrocyanic acid.